Hello, and thank you very much for coming to this session about injecting security controls in software applications. In most companies, the security is a checkbox, and it's there for compliance regulations reasons. We define the policies that contains the CWEs each company is interested to comply with, SQL injection, cross-site scripting, or any other CWE each company is interested to comply with. And this is how we think of security, like a checkbox that we must tick. So the software is then accepted and released in production, in particular in those companies where there is a security release gate. The result of this approach is that a high number of insecure applications is still developed, and injection is still king. In the latest OWASP Top 10 2017, the injection is still in pole position at #1. So is there anything else that we can do? And that's what I'm going to explore as part of this presentation, where I'm going to look at vulnerabilities from a different angle. We will decompose the vulnerabilities into the security controls that prevent them and are familiar to developers and can be used in the software development cycle. And we will focusing on the CWEs, which can be measured only after the software is developed at the end. To focus instead on the security controls that prevent them, are familiar to developers, and can be used from the beginning. A little bit about myself. My name is KATY, and I come from a software development background, where in my previous life I have managed and created teams of developers. And that's where I got involved into the OWASP Top 10 Proactive Controls, which is an OWASP project for developers by developers. I currently work as application security consultant at Veracode, and this is where I help developers around the world to secure their applications. The first category of vulnerabilities that I will tackle, yes, it's injection. This is still one of the most common vulnerabilities found in software applications. As a category, this is a large category, and it contains multiple types of injection. And you have command injection, cross-site scripting, XML, code injection, LDAP injection, SQL injection, just to name a few injections. And if we go into each of these classifications, then depending on the type of the injection, you can have further classification. You can have inbound injection, out-of-band injection. So it can become quite complicated. And it makes it really difficult for developers to think of all of these type of injections while they write their code and all of these type of attacks. If we go to a basic definition of what the injection is, just go back to the basics. The injection occurs when some data is combined with a sort of a syntax. That result is then sent to the parser, and that is when it ends up being executed as code. So the data, which is not necessarily only from get and post, but it's also from HTTP headers, file uploads, data from the database, configuration files. So when all this data from all this wide range of sources is combined with a sort of a syntax, that result is sent to a parser, which, if we store data to the database, that is the SQL parser. If we render a web page, that is the HTML parser, or the browser. And that is when we end up with code, with data executed as part of the code. So I will take this view, and I will flip it to focus on the red bit, the output, which ends up being executed as code. So if in the case of the SQL injection, like I said, this occurs when you have the input, which is combined with the SQL query. That is sent to the parser, and that's when it ends up being executed as SQL command. The primary defense for this is to parameterize the queries, to separate the input from the actual SQL command before sending it to the SQL parser. This is the primary control to parameterize the query. But as defense in that, we still have to validate the input. And ideally, we must do both of them at the same time. In the case of cross-site scripting, the primary control for this one is to contextually encode the data before creating the HTML document that is sent to the HTML parser. And this is the primary control. But as defense in that, we still have to validate the input. And similarly for the case of the XML injection, LDAP injection, and command injection. In the case of the command injection, depending on language use, ideally we would parameterize the data if that is available. If not, then contextually encode the output before sending it to the parser to neutralize the characters that can trigger the code injection, the command injection. So rather than focusing on all these type of injections which can be quite overwhelming, instead we can choose to focus as a primary control always to parameterize the data. If that's not available, contextually encode the output to neutralize the characters that can trigger the injection. But as defense in that, we still have to validate the input. The input validation helps to reduce the attack surface. And it's more efficient if we do this when data enters the application. In the case of the MVC controller, this point, in the case of the MVC, this point is in the controller. And that's where it's best to perform the input validation. And we have to do this both. By doing this in a consistent manner, both of them, we are able to prevent vulnerabilities that developers might not be aware of. A good example for this is the second-order SQL injection, which is the injection where the injection payload stays dormant into the database until it finds the right environment to be exploited. The next category that I will tackle is vulnerable components. Or in other words, using software components with known vulnerabilities. Today, we are pretty good at identifying the libraries that are part of a software, identifying the vulnerabilities which are part of our libraries. And we are pretty good on this because we have either open source tools, like a dependency check, or commercial tools. But the problem that I see out there is that we end up with a report. In the case of the Java application, this can be like a few hundred libraries. And it takes a long time to actually do something about this. And that's where the problem is. And the software that has this problem is the type of software that no developer wants to touch, because if they change something in one place of the software, they are going to break something in a different part of the software. As a result, it's difficult to test. It might have some few tests, minimal coverage. It is difficult, and all of this means that it is difficult to upgrade and leads to a high level of technical debt. And that's where the problem is. The type of software that has this high number of vulnerable components is the type of software that has a high level of technical debt. So is there anything else that we can do about this? And I'll go for this. There is a strong connection between software development and how to deal with this from a security, to deal with these security issues. And I will explore for these three types of components. The first one is an open source component like that is commonly used. But I will not focus only on open source components because the problem is not only there. I will also consider an API from a vendor, and also the scenario, which is quite common in large companies, where you have a team that develops a package and then that is reused on multiple applications within the same company. So the first scenario of an open source library, and the very common one is to bring in a logging library. And like any ready-made library, it has a wealth of functionality. And most likely, your software will not need all of this functionality. For example, in the case of logging, you only want to focus on 3 levels of logging, one debugging info. So for this scenario, when you want to expose into your application only a subset of the functionality, and you want to hide unwanted behavior, a good software design pattern that can be used is a simple wrapper. This helps you to expose only what you want, hide unwanted behavior, and this is a good way to reduce the attack surface into your software. But it's also a very good design pattern because it helps you out to upgrade or even replace without much penalty these libraries if they become obsolete. The next one that I'm going to consider is to implement a vendor API. A very good example of this, in particular, in the case of the e-commerce application, is the payment gateway, where it's highly likely that a website will have more than one payment gateway at the same time. Now, from a security point of view, we have to be aware that there is a trend out there at the moment. And this is that rather than breaching the target, we can breach the partner of the target. So again, this is another way that we need to be on top of. And in the case of these vendor APIs, we need a way that if one of our partners has been breached, we can get into the control of our software. Now, in the case of a payment gateway, it's highly likely that the vendor API, it has its own methods, and your software will have its own transactional methods. So for this, and it needs a way of conversion. For this scenario where you need to convert from the provided interface to the required interface, the one that your software requires, a good design pattern is the adapter design pattern. The benefit of this one is that it can work with multiple adaptees at the same time, and it allows you to quickly switch between them. So if one of the partners is breached, then this is something that, again, helps you out to get into the control of your components. And the last example is to implement a package that has been developed by another team within the same company. A good example for this is a single sign-on. And then this is reused for every application within the same company. This can, the example of single sign-on, this can be quite complex sometimes. So for this scenario, when you actually want to simplify the interaction between your own software and the complex subsystem, a good design pattern is the facade design pattern. It still offers the same benefits of actually getting into control. You have the facade class where you actually can get into the control of your libraries, and you can easily upgrade if something happens. So if we are to summarize, secure software starts from the design, from the point when we have chosen how we are going to implement when we bring in a component. From that point, the security of the software starts. So we can choose to use just a simple wrapper when we want to expose into our software only a subset from the functionality provider and hide unwanted behavior. We can choose the adapter design pattern when we want to convert from the provided interface to the required interface, and the facade when we want to simplify between the complex subsystem and our own software. This design pattern also helps with legacy application. to get into control of those type of application and again, improve and upgrade your components. And another type of issue that I'm going to discuss is about intrusion detection, or better said, the lack of it. The problem that we have out there is that logging, fail logins, high-level transactions are not logged. If there is some sort of a logging, then the format is not consistent enough to allow an organization to centralize all of these logs and process them in an automatic manner to get, in a reasonable amount of time, some information about any suspicious activity. As a result of these two problems, not enough information, security information, and not consistent format, there are many APIs and applications out there that are simply not monitored. To put it simply, if a pen tester is able to get into a system without being detected, this is a good indication that there is not enough monitoring and intrusion detection in place. So what can we do from a software development point of view? For this, for developers, we have the security logging. This is the control for developers to log security information during the runtime operation of an application. Now, this has been introduced by the OWASP Top 10 Proactive Controls team in 2016, and then it has been taken over into the OWASP Top 10 2017 as A10. So let's go a little bit more in detail to have a better understanding what this means. According to, there is a very good project, OWASP project, which is the App Sensor. And there are 6 types of detection points that are considered good attack identifiers. And these are the authorization and authentication failures, client-side input validation bypasses and whitelist input validation failures, obvious code injection attacks, like obvious SQL injection strings, and the high rate of function use. For example, you have a high number of page requests in a very short period of time. So let's go through a little bit more to some of these examples. Now, in the case of a request, if the application expects to receive POST, but instead it receives GET, this is a very good indication that somebody has intercepted that communication and has intentionally changed from POST to GET. This type of anomaly, this exception, should be logged. Equally, if the application receives extra form or URL parameters, and something that a pen tester will always do is to add, for example, debug equal true, just to see what happens. If this happens, this is another example of an exception that should be logged. In the case of authentication, if the application expects to receive 2 parameters, the username and the password, but instead receives only one of them, the username, because the password has been intentionally removed, this is another example of an exception that should be logged. Or if there are extra additional parameters that are received during authentication. A good example of this, and something that a pen tester will try, is admin equal true. If this happens, this is another example of an exception that should be logged. And in the case of the request exceptions, for example, if your server-side validation fails, despite the fact that you have a client-side validation, and a very simple example of this one, you have on the client side a web form. In one of the elements of the form, you have an attribute, maximum length. However, when that string reaches the server side, the length of the string is greater than the one that has been defined in the client. This is a very good indicator that somebody has intercepted that communication since it has left the client, intentionally changed that string. And this is another example of an exception that should be logged. And equally, in the case of non-editable form fields, like hidden fields, radio buttons, this as well should be validated, and these are good examples of exceptions that should be logged when the validation fails. Now, these are just a few examples. If you want to have a better understanding and to see more examples, the best for this is the AppSensor project, OWASP AppSensor project. Now, there are two parts of this project. There is a tool, and there is a documentation. This research, and this refers to the documentation part of the project, which is something that a developer needs to put into their own application as part of their business logic. And by putting this, having this verification in place and putting this into our own software, what we're actually doing is we just validate that the software receives what it expects. However, when this does not happen, and we have these exceptions, by having this into the software, what we are giving to the software, we are giving it the mechanism to respond in real time to possible identified attacks. These attacks that we have identified, and the software can reduce or even stop these attacks, depending on how we choose to write the software. So if we are to recap what we have discussed until now, every time data enters our application, and it's not only from GET or POST, it's from a wide variety of sources, we should validate that data at the point of entering your application. Any exceptions that we find, those should be logged in a constant format to give the software the mechanisms to respond in real time to possible identified attacks. Any output should be contextually encoded, and when you store data into the database, we should parameterize the queries. If we really need to use to access operating system commands, ideally we should not, but if we really, really need to, we should parameterize the data to separate the input from the actual command. And every time we bring in a library, we should encapsulate it and use a software design patterns that help us to get into control of our components, to upgrade them or even replace them without much penalty whenever a new vulnerability is found. Now, are these the only controls that we should be using? Definitely not. And depending on how you want to define your policy, we can add to this. So, for example, if your application needs to store data, sensitive data, we should encrypt it and then store the keys into dedicated key management solutions. And if you want, for example, to amend your policy in order to add to it some of the latest OWASP top 10, like let's say, for example, the XXC, XML external entity, or CWE 611, then the control for that is to harden the SQL parser before parsing an XML document. And we can add that one to our list of security controls. Now, what I would like you to take away is that we need to have policies where we define the CWEs. But instead of focusing on the CWEs, which can be measured only at the end, after the software has been developed, instead, let's focus on the security controls that prevent this, are familiar to developers and can be used from the beginning. And it's also important to use this on a consistent manner all the time in the software. It's not a matter of choosing which one of them. Ideally, we must use them, all of them, because we have to remember that an attacker needs only one flaw in order to bring down a system. As developers, we have to defend everything. And using them on a consistent manner, it helps to prevent other vulnerabilities that a developer might not necessarily be aware of. Also, it's very important to verify that, one, we have implemented them, and we have implemented them correctly to effectively prevent these CWEs. And hopefully, on the next OWASP Top 10, we are not going to have injection as number 1. Thank you very much. Any questions? Yes, so it's about using a wrapper to reduce the attack surface, yes. If the what? So that type of design pattern in the facade, it gives you that one point where you can actually apply extra controls if you can't necessarily upgrade that library within the time. So, for example, you can add extra validation or extra other things into that one for a period of time. Now, there is a good book. It's called The Clean Book, The Clean Code, and it's by Robert C. Martin. And that gives a very good example of how to actually implement this in the more detail. Ideally, when you implement this, you'd have tests, unit tests, because when you're bringing a library, you must know the functionality that you are using into your own software. You might not necessarily know, you can't know what exactly that library does as an entire, but you are, as a developer, are responsible to know the functionality that you import in your software. And for this, the only way that you can achieve it is with tests. And if you need to upgrade, then having those tests in place, the unit test and the functional test, helps you out. It gives you that assurance that your software, after either putting controls or upgrading yours, is still going to work as you design it to work.
Yeah, I wanted to you to expand a little bit on the injection, maybe, problem. The model that you propose is elegant, but I feel it might be a little bit simplified, of course, like any model. For example, validating input, of course, as a defense in depth and whatever, logging exceptions, and then encoding the output as preventing injection vulnerabilities in general. However, if you apply that consistently, your application no longer can output HTML, because if you intend to encode every output, HTML can, I mean, as for XSS and HTML, the HTML output needs to be escaped, and therefore your application cannot produce outputs that are HTML at all, right? Which is obviously not what you want. I mean, you want the application to work and encode only the output that is, let's say, user or attacker controlled, right? In order not to have data converted into code, right? That's the model, if I understand correctly.
Yeah, but you need to also consider data from the database in the case of output. That's another
but all of the inputs, of course, yes.
So, yeah, and that, I think this is important to identify which is the data that can be tampered with. And that's the one that you actually want to encode just before you create the HTML document that is sent to the parser.
Exactly, yes. But then that becomes a taint tracking problem, essentially. Because you want to assure in your application that all of the outputs that are, or all of the inputs that are tamperable need to be, consistently escaped or, turned into parameterized queries or whatever. And this is something that we don't yet know how to achieve comprehensively.
So,
and I feel this is the real cause of the vulnerability, especially for XSS or even DOM-based XSS, where you don't even have all of the security controls available. Because the API is on client side, for example, so you cannot hook into all of the APIs, for example.
Mm-hmm. So is that a question about how do you trace the tainted data?
Yes, especially on I feel this is the missing part.
So for that one, you would consider anything that can be changed as possible taint, and you will treat it the same. Possible taint can be can come from data from the database, data from configuration file. You might say that they are on a server, but if the server has been compromised, and a good example for this was the data breach in Marriott, or the company that they acquired, where the attacker has been there for 4 years. So you don't know what's on your network or who is on your network. So you should consider the configuration files like data that can be tainted, and then all of that one should be treated in the same way. If you use that data to create an HTML document, this still has to be encoded.
Yes, I understand that, but I guess the question I'm asking is more, while it is possible, and people are doing that, to taint the data, to implement a taint tracking engine, essentially, in your, let's say, server-side code with whatever technology stacks you're using, it would be Java, PHP, or whatever, this one is doable. Whereas for, say, injection on the client side or DOM-based XSS, you don't really have that. Like, you can't analyze the JavaScript code enough. You can't statically analyze it in order to successfully taint the data on the client in the browser. Therefore, you cannot, with this approach only, address the DOM-based XSS.
For that one, what you'd usually do, you ensure that in sync points, you actually have data that is validated either on even on the client side in JavaScript. So if you have something that comes either from a URL and then you use it into a sync, which can trigger a type of a cross-site scripting, domestic XSS, you still validate it. There are more, if you don't know, then probably a good, you might use a library that will deal with that one. And there is a library of that Mario, DOM parser, that Mario created that can deal with those more.
DOM purifier, yeah.
Yeah, DOM purifier that can deal with those type of more complex type of possible taints.
Okay, thank you.
Okay, thank you very much.